Okay, let's start off with everyone's favorite number sequence, that is the Fibonacci numbers. So Fibonacci numbers are very simple. Simply put, we have a base case, which is that the zeroth Fibonacci number is simply equal to 0. The first Fibonacci number is equal to 1, and we and for the Fibonacci numbers that come afterwards, for instance, Fib2 would simply be equal to the previous two Fibonacci numbers. So Fibonacci 2 is equal to 0 plus 1, which is 1. Fibonacci 3 is equal to 1 plus 1, which is 2. Fibonacci 4 is equal to 1 plus 2, which is 3. Fibonacci 5 is equal to 2 plus 3, which is 5. Fibonacci 6 is equal to 3 plus 5, which is 8. Fibonacci 7 is equal to 8 plus 5, which is 13, and so on. Okay, so a beautifully simple number sequence, and it has many interesting properties in all areas of mathematics. In fact, it's so widely spread that there is a journal called the Fibonacci Quarterly. So, kind of cool things about Fibonacci sequence that you might not know. You may not know, while it is possible to generate the nth Fibonacci number using this formula, you would have to go through each particular formula. You would have to go through every single number up to n in order to get the nth Fibonacci number, which is burdensome. Okay. Turns out a famous mathematician named Beignet solved an analytic expression to get the nth Fibonacci number. And Beignet's formula is shown here. Simply put, Beignet observed that the difference, the ratio between subsequent Fibonacci numbers, goes towards the golden ratio. And for those of you that don't know, the golden ratio is a fundamental number, like pi in mathematics, and the golden ratio is equal to 1.618 approximately. And Beignet noticed that as the Fibonacci numbers go, as n goes to infinity, the ratio between Fibonacci numbers goes to the golden ratio. Using this idea, he created Beignet's formula, which simply provides a pretty damn good estimate of what the nth Fibonacci number is. Obviously, it's slightly less ideal for the earlier Fibonacci numbers, but as n grows, the analytic formula is pretty much dead on. Kind of cool little thing there. But for our purposes, we're looking at the Fibonacci sequence because we want to study recursion, right? So, how do we write the Fibonacci sequence, Fibonacci numbers recursively, right? Suppose we are given an input n and we want to generate the nth Fibonacci number. How do we do that? Well, I mean, the Fibonacci numbers themselves are a recursive sequence, so we just write that recursive sequence in code. Okay, pretty simple. So, what is the running time of the Fibonacci of this function? Now, how do we analyze running time in recurrent expressions? Well, we got to know how much work is done at every call. So the amount of work done here, it's pretty much only one comparison. So the amount of work done here is along the lines of O of 1. And so if we analyze the expression tree at n, and then we call two instances of n minus 1, two instances of fib, one for n minus 1, one for n minus 2. So we do n minus 1, n minus 2, and then we go further down, n minus 2, n minus 3, n minus 3, n minus 4, and so on. We notice that at each of these levels, we have one work. Oh, I'm sorry. At each of these levels, we go from 1 work over here to 2 work to 4 work, and so on. Okay, so this recursive function is leaf dominated. The recurrence that we would write for this recursive function is t to the n is equal to t of n minus 1 plus t of n minus 2 plus O of 1. And we say that this recurrence is leaf dominated, meaning that the recurrence is bounded by the number of leaves at the end of the tree. And how many leaves are there at the very bottom of the tree? Well, it's not perfect. This isn't a perfect approximation, but there are approximately 2 to the n leaves, right? So we say that the running time for the Fibonacci, that t of n is equal to O of 2 to the n, and so the running time of the Fibonacci sequence is roughly exponential, 2 to the n. However, we could get if we solve this expression exactly, we could get a closer bound by using the golden ratio. Okay, so for my class, it would be sufficient just to say that the recurrence is bound by O of 2 to the n, but you could solve this recurrence exactly, and you would get approximately theta of golden to the n. Okay, so the point of this whole thing is that this is an inefficient function. This causes exponential growth, and in computing, exponential growth is a bad thing. So, can we do better? That's the question, and that's what we need to find out.